So today we're discussing analysis of bending of beams. The objective is to derive the bending equation and then apply it on some scenarios or some examples that we're going to pick. So look at some application as well. So previously, we had already talked about the shear force and bending moment diagrams where we did the calculations. You could be calculating for the bending moment diagrams, or you calculate for the shear forces. Then later on, you draw both the shear forces and also the bending moments. But today, we'll just go straight to what is called the bending equation, and then we apply it. Now, when you're analyzing the bending equation, or in this bending theory, in the theory of bending, there's some assumptions that we make. First of all, we say that we assume that the material of the beam or the material of that section under analysis is uniform, is the same, is homogeneous. Of course, we're saying that in reality, this may not be true because there could be some additives here and there, but this is an assumption we take. The next one is that we assume that the stress is proportional to the strain, and it has to be within the elastic limit. We don't exceed this. And the third assumption is that whether you're talking about compression or tension, the Young's modulus is supposed to be the same for either of the two. Then also that the transverse of the beam, which is plane before bending, remains the same even after the bending has taken place. The other assumption is that there's no resultant pull or push on the cross-section of the beam. But again, emphasizing that that's why they are assumptions. In reality, we may have some variance to this. Then we also assume that the laws that are applied in the plane of bending. And we also assume that the transverse section of the beam is symmetrical about the line passing through the center of gravity in the plane of bending. We realize that when a material is being acted upon by force, this does not really happen like that. The symmetry is subjective, and in reality, it's not very easy to achieve. So with this assumption, it makes our analysis matter. Then also, when we are analyzing the theory of bending, we're saying that that material is going to bend and to make a curve with some radius. So here, the assumption is that the radius of that curve or the curvature of that beam or section before bending is very large compared to its transverse dimensions. That's another analysis. Though we've said in reality, we may have some variance when you go to the actual application. But for the sake of simplifying and making sure that we analyze this correctly, we make all these assumptions. So before you go to the bending equation, what are some of the assumptions that are put forward in coming up with the equation that we are going to derive? These are the ones we've talked about. So here we are considering a beam. Now look at this section. What you have is PQ and MN before the bending action. So after the bending moment has been applied, then you notice it bends like that, making a curve of radius R. The distance from some point up to the center, this is our center AB, representing the neutral axis where before and after the bending, the material remains the same. Now, with this, we are saying that what you will notice is that up here on top, right here on top, P dash Q dash, what you have there is basically the compression. Below this neutral axis, it's tension. So if you're moving from compression to tension, you have to pass through a transition. We're talking about passing through a point where things are neither in tension or rather the strands of the material, the grains of the material are not in tension, they're also not in compression. They're neither being taut, neither being compressed. So that is the neutral axis. So we expect that point to have neither of those. With this in mind, you notice that PQ, this PQ on top, is longer than P dash Q dash because this has been compressed. If this was outside, on the other side of the beam where the material is in tension, we're going to expect that this is actually bigger than that initial one. So when we're trying to get the strain as a result of this action, we will subtract this big one minus that. In other words, we'll say P dash Q dash subtracted from PQ. And then we apply the geometry of this to ensure that we can get the answer. So we start with the strain itself. We say that strain is change in length over original length. What we said is that PQ minus P dash Q dash. So here we're saying that when you compare the two, you notice that this is bigger than that. So when we subtract like that, it will give us some positive answer. All we want is to represent this change in length we have there. Now, with that in mind, we can also now look at this PQ. It's the original length. So that's the one we still have there. Then here we're noticing that PQ is the same as M dash N dash, which is given by R theta. The length of the arc, this one, let me just go back. R from O to M dash multiplied by the angle theta gives us the length MN. M dash, N dash. So the length of an arc, as long as the angle there is in radians, when you multiply the radius by that, you are okay, you get that length. The same thing with P dash Q dash. To get this one, you're going to now multiply OP by the angle theta. But unfortunately, to get this one, you have to involve this distance, this y. So you say the total radius r minus y. It will give you this from P to there. Then you can multiply it by theta. What are we talking about? This is what we have here now. We're saying here, of course, we've just replaced for PQ is r theta, but P dash Q dash is the one we're saying is r minus y, then multiplied by theta. Then when you open the brackets, actually this now becomes r theta minus y theta. That's what it may become. But anyway, for now, let's see what we do. So here, this is the one. Expanding this will give us that. Meaning that if I have to take away now this minus, which is outside, multiplied by that, I'll still have negative r theta. And if I multiply again negative by y theta by negative y theta, this will be positive y theta, which will mean that this is what I have now. This one as well as this, r theta take away r theta, I get 0, they cancel. Just like I remain with y theta over r theta. So what do? There's a theta here as well as another theta there. So this can cancel. What have I been looking for? It's just strain right here. Now what do I do with the strain? It means that my strain therefore is simply y over r. But strain is not given by this expression. The strain I know is given by Young's, rather stress over Young's modulus. I also know that this strain is also given by the definition of Young's modulus, which is stress over Young's modulus from that equation. So meaning I already have the first and the second sets expressed like in that way. We're saying stress when we refer to the definition of Young's modulus, it's also given by, strain is given by stress over Young's modulus. So we can now just bring them together. We say strain is Y over R is equal to stress over Young's modulus. All we can do now is to rearrange it in a manner that will make our progression much easier. So we'll say E over R is equal to stress over Y. And we call this as our startup equation, as our equation 1. Next, I consider a small elemental area, delta A, at a distance Y. So with that, I already start. What I will notice is that when I say stress over Y multiplied by Y, this Y can easily cancel out. I'm not going to change anything. So it's okay like that. Now, deliberately, I've done this because I know I can easily relate this, this thing I have here to that. So what do I do next with that in mind? I can say, since this is stress over Y, then I'll put E over R according to that equation first of all. Then I substitute. Where there was stress over Y, I put E over R. The Y still remains Y. Now here, I'm multiplying by delta A. Why I've done this is that I'm multiplying stress by area. When I multiply stress by area, I get a force. For the force which is acting on the elemental area. Then I'm not just interested in the force. I want the moment. Remember, here the target is to get our bending equation. So I need to arrive at that moment. So what do I do with this expression? So I can now multiply this force by some distance, something representing the radius. So I say dF times y, meaning that the whole of this expression I have up here, I multiply by y. So E over Ry multiplied by delta A, then y has just now come in. We are talking about delta M. Then I can now multiply y by y, which gives me y squared. So E over R, then this y squared delta A. Now this was the moment acting on the elemental area. So what do I do? That small moment. To get this full moment acting on the whole section, I have to sum up all those mini elements that are there acting. So summation of those small moments will give me for the bigger section now. So summation of E over R y squared delta A gives me our M. Now with that already, I will remember that the second moment of area about the neutral axis is given by summation of y squared delta A. Just here, I just separated them. So with that in mind, what I'm going to do now is the whole of this side where there is y squared delta A will be represented by I. So it becomes M equals E over R, then there's I. Looking back at our standard results, we already had E over R. So what I will do is divide through by I. So M divided by I is equal to E divided by R. So that gives me the second part of the equation. Now that I have this, I can combine the first set of results and this one I'm having equation 1 and equation 7, whether if it was equation 2. So having done that, I can now arrive at M over I is equal to E over R is equal to stress over Y. The first set we had was E over R is equal to stress over Y. So we've just now managed to find this other one, which is M over I. This is our bending equation. If you're required to find this from first principles from scratch, that's how you go about it. And then once you have arrived at this one, you've reached the standard result that you're looking for. So what do we need to do now? Let's see how we can apply this. Let's see how this can now be applied. We have an example here. Example 1. So here is a beam, a section of 250 millimeters in depth and 150 millimeters in the width. then the bending moment, the maximum bending moment is 750 kilonewton meters. We are required to calculate the stress in the beam, the radius of the curve, and the longitudinal stress acting at 65 millimeters from the top surface. As per tradition, let's start with by finding the data, information provided. So what information have we been given in this case? First of all, we have the width B, 0.15. It was 150 millimeters. D, representing the depth, that's 0.25 meters. Then we have the moment, which is 750 kilonewton meters, which is 750. The kilo is 1,000, so it's a 750,000 Newton meters. Then E is 200 by 10 power 9 pascals. Further, we can get to A. In A, we didn't find the moment of inertia about the neutral axis. So we say BD cubed over 12. Our B is 0.15 by 0.25 cubic over 12. So that gives us the answer 1.953 by 10 power negative 4 meters, quadrometers, or just meter power 4. Then to get Y, we said D over 2. Whether it's, even if it's the diameter, when we're talking about the maximum stress, we still say D over 2. In this case, this is representing the depth. So D over 2. Our D was 250 millimeters, which is at 0.25. When you divide it by 2, you get 0.125 meters. Then we can pick up the second set. M over I is equal to stress over Y. Remember, the full bending equation went further, and this is also equal to E over R. E over R, just like that. So here, you may not use the full set like that. You can always pick any two sets. In this case, we've picked the first two. M over I is stress over Y. So from there, we are looking for stress. When you make stress the subject, you end up with, it's like you end up multiplying Y both sides. So you have My over I, My divided by I. And then we just do the substitution. Our M representing the moment, according to the data, this was 750,000 Newton meters. Then the Y was 0.125, I 1.953 by 10 power negative 4. And our answer is 4.8 by 10 power 8 pascals, or you can say newtons per square meter. But it was asking us to find the bending stress or simply the maximum stress that this material is experiencing under such conditions. Let's pick up B. In B, we need the radius. So the radius, we pick M over I is equal to E over R, and we make R the subject, which gives us R equals EI divided by M when we do the cross multiplication and isolate the R. So EI over M. So let's do the substitution. E is 200 by 10 power 9. I is 1.953 by 10 negative 4. M is 750,000. So with this, our answer comes out as 52.08 meters. If you look at the assumptions that we had, one of them was saying that the radius that we get is usually bigger than the dimensions of the material we're dealing with. This is what you can see there. Either way, that is our radius. Then we can now try to find the stress at a point which is 65 millimeters from the top surface. 65 millimeters from the top surface What it means is that we're talking about moving 65 millimeters from that top surface coming inside the material. So there. Now, this is not our y. This is not our new y because y is measured from the neutral axis up to where you are trying to find the stress. So what are we going to do? The y we're looking for is the one from there up to that point. 65 millimeters, when you convert it to meters, it becomes 0.065 because you divide by 1,000. So with that, it means we have to subtract now from this total, which we had as 0.125. When you subtract 0.065 from 0.125, you get 0.06. 0.06. This is our new y. That being the case, you can now make stress a subject. So you have my dash representing the new y over I, my over I. So with that, we can go ahead again, do the substitution. M is the moment, so 750,000. Our new y is 0.06. Our I is 1.953 by 10 power negative 4. Already you can see that the full set is now with us. All we need to do, plug this in the calculator. Let's see what this can give us. Once again, I keep saying that with the calculators, check through the values. If you see anything that looks like straying away from the usual numbers, always plant it in the comment section. Let me know so that we refine where we could have perhaps put the numbers together. So in this case, our stress comes out as 230, 414746, like 2.3 by 10 power 8. Now, you will notice that this stress is actually smaller than the other stress we had because we are moving away from there, going towards the center. At the center, at the neutral axis, the stress is actually 0. So from here, going towards the center, the maximum stress we had was on top there. That's the one we calculated. Then the one we have here is supposed to be small. If things switch the other way around, just check your values, check your working, or suspect your calculator, either of those. But remember, we are approaching 0 at the center. So that number should respond to that. Let's pick up another one. Here we have a section, the depth is 200 millimeters. We've also been given the moment of inertia about the neutral axis, 2.26 by 10 to the power negative 5. Then the longest span over which this is over which a UDL can be loaded. The UDL is 4 kilonewtons per meter, and the stress is 125 meganewtons per square meter. This is a scenario. What we are trying to find is simply the length. We just need to find the length of this beam. Over what length are we loading this UDL for us to achieve these conditions? What information do we have? D, 0.2, I, 2.26 by 10 power negative 5. This W, which is representing the UDL, unit newtons per meter, 4,000. Then the bending stress is 125 megapascals, which is 125 by 10 power 6 pascals. We still need to clean up our data because in our data, we didn't finish up with Y. Y we said is supposed to be D over 2. So D is 0.2 divided by 2. Our answer is 0.1. So that's D over 2. Then we go back again to the same equation that we had, which is M over I is equal to stress over Y. M over I equals stress over Y. So making M the subject, you have stress I over Y, meaning we just do the usual cross multiplying to make sure that this there. Then we are here. Substituting, we have stress, which is 125 by 10 power 6, by I, which is 2.26 by 10 power negative 5, y is 0.1. Our moment is 28,250. But let's get this straight. The question did not ask us to look for the moment, not at all. It's like you go to the market, you're told to go and find bread, and then you go ahead and look for charcoal or something else. That's not what you're looking for. In this case, the question was specific. It needed the span, the longest span over which the UDL can be spread. So we're looking for the length of this beam, the length of this material. What is the length of this section? What is the length of this beam? Now let's get this straight. To get the length of the UDL, we have to understand one thing. Here is my beam. UDL is usually represented in this format, but it can also have other ways. At the end, all we know is the unit, the force per unit length will be provided. And then we are told that this is our loading, which is W. And what unit? In newtons per meter. Now the total length of this from there all the way to there, this is actually L. When you decide to draw this, when you decide to analyze this, what you'll find is that actually the moment we're looking at, the maximum moment that this UDL can have happens at the center, which is at actually L over 2. This is where it happens. Now, a UDL comes with a unit. The unit is Newton per meter. Newton per meter. In this case, we were told that is 4,000 newtons per meter. So Newton per meter, meaning that I want the force responsible for this. The way we treat moments is when I say I'm standing here, I look back. So this becomes L over 2 as my length. So what do we do to get the force? We multiply this by the length that you are dealing with. In this case, my length at this point where I'm standing is L over 2. So the force at the center where I have maximum moment is actually L over 2. Now, it's at L over 2. I multiply by the total length, the unit which I have as W, or I can even do it the other one, it's the same thing. So I multiply W by L over 2. W by L over 2, just like that. This gives me the force because this, when I multiply the length by the force per unit length, the meters cancel, I just remain with the newtons. Now, because it's from here up to there, it means this length that I've already cut is going to be, the UDL within this length is going to be concentrated at the center of this. You can even write it down using dotted lines like that. So my UDL, the one I've cut, where I'm standing, where I expect to have a maximum bending moment, it's only going to use this. To get the force, I multiply this by L over 2, which is the length I have. To get the distance, I'll call it the distance. It is actually half the length. It is at the center of this length I have here. So I'm going to say L over 2 times what? Times half. In other words, I don't even need to stress like that. When you notice that this is L over 2, what is half of L over 2? It's simply a quarter. In fact, I now have L on top over 2 times 2, which gives me a 4. So that's L over 4. So when I'm looking for a moment, I'm going to say my moment is therefore equal to W, or simply before I talk about W, it's F times D. So I'll say my moment is equal to force times the perpendicular distance, F multiplied by the D. Now, what is my F? This F is WL over 2. Then what is my D? My D is this one I have here, which is L over 4. So I multiply by the distance, the perpendicular distance, which is simply L divided by 4. Let's put them together. L times L is going to give me L squared. So I'll have, therefore, my moment at any given point, I'll start with this same W, which I have. Then L times L is L squared. Then what else do I have? 2 times 4 gives me 8. So that's how come I have 8 there. Now, that is how come we are saying for a UDL, as long as it's just a UDL, our moment at any given point, our moment that we're looking for, the maximum moment that we want is given by WL squared over 8. WL squared over 8. Now remember, W has been given, this other one is just a number, the moment we just calculated. We're looking for L. So if you want, you can do the substitution, or you proceed to this. You make L the subject of the formula. So when you make L the subject of the formula, you get square root of 8m over W as your expression. So 8m over W. So 8 times 28, 250. Divide everything by 4,000. Square root of what you get, the answer is L is 7.517. That is the length of your beam, the L that we're looking for, this L. So that is how you handle this type of question, step by step. Now here you will notice that we've just talked about cases where this is a rectangular cross-section and name it. What if it's a hollow shaft? In the case of a solid or hollow shaft, the only additive we are having is that the moment of inertia about the neutral axis is I pi d4 over 64. This is for a solid shaft. If it's a hollow shaft, you subtract. It will be pi over 64. Then inside the brackets, you're going to have capital letter D power 4 minus small letter d raised to power 4. And one thing is that even the rectangular sections we're talking about, if it's hollow, you say BD cubed, these capital letters minus BD cubed in small letters, everything over 12. Then you still get the same results. So let's look at an example for this one also. Here we have a shaft, external diameter 60 millimeters, the internal diameter 20 millimeters. If the bending stress is limited to 120 megapascals, determine the allowable bending moment for the shaft. So here we again pick up the data. We have D, which is the diameter, 0.06 meters. This is the external diameter or the major diameter or the outer diameter. The inner diameter representing the hollow is 0.02 meters. The stress is 120 megapascals, which is 120 by 10 power 6. Then we already said Y is D over 2. Now you could be wondering, here we have two diameters. We have the one inside as well as the other one outside. So which of them do we pick when we're looking at D? We pick the one outside because we want the stress there, the maximum stress. I mean, we're analyzing with this being limited to representing the maximum value of the stress. So we pick the bigger diameter, not the smaller one. So that's why we're saying d over 2, we say 0.06 divided by 2, and our y becomes 0.03. To get our second moment, rather the moment of inertia about the neutral axis, we go ahead and say pi over 64. Then inside the brackets, we have d power 4 minus d power 4, capital, small, presenting the bigger one minus the smaller one. So pi over 64, inside the brackets, we have 0.06 raised to power 4 minus 0.02 raised to power 4. Result, 6.283 by 10 power negative 7. Okay, so that gives us our moment of inertia about the neutral axis. So now that we've found this one, what do we do next? We can proceed now to the next one. In the working, we're saying m over I is equal to stress over y. And making m the subject, we have stress I over y. And we can just go ahead and do the substitution. We always say that if you want, you can proceed to substitute at this same stage. But here we are. So stress is 120 by 10 power 6. I 6.283 by 10 power negative 7 divided by 0.03. And our answer is 2513.274 Newton meters. So this is our analysis of the bending equation. And take your time to answer the exercise, this one. There's also another exercise that we left up there, presenting this one here with the answers already planted. So take your time to answer them. And if you feel there's something that needs my attention, feel free to alert me in the comment section, or you can reach out.